Today we're going to be talking about least squares regression lines. So hopefully you have your notes in front of you, maybe a calculator because you may need one in a little bit, and let's get started. So we're going to start off. A regression line describes how a response variable, remember response variables are the y, they are the dependent variables, how they change as an explanatory variable, or the x, the independent variable, changes. We call this bivariate data because we have two different variables, and we are using x to predict y. The least squares regression line, we refer to this as an LSRL. It is the line that gives the best fit to the data set. It is also the line that minimizes the sum of the squares of the deviations from the line. Now that sounds kind of complicated, the sum of the squares of the deviations from the line. And I'm going to show you a picture in a minute that explains that a little bit better. And we'll probably also be doing something in class to explain that a little bit better as well. This is the equation for what a least squares regression line is. The symbol on the y is the y hat. It's a little asterisk above, a little y hat symbol, equals a plus bx. It is the exact same thing as what you did in Algebra 1 and Algebra 2 when you do y equals mx plus b. The b is the slope, and the a in this case is the y-intercept. The y hat means the predicted value of y. When you're writing this in context, you always want to make sure you include that this is a predicted value, and you always want to be sure that you put the hat on the y. B is the slope. It's the amount by which y increases when x increases by 1 unit. And that's an important phrase because you do have to write these things in context, and that's the phrasing you want to use when you're describing the slope. A, of course, is the y-intercept. It is the height of the line when x equals 0. And in some situations, the y-intercept will have no meaning at all, so you have to be very careful about that when you're explaining in context. The least squares regression line makes the sum of the squares of the distances of the data points from the line as small as possible. So if you were to try and draw, the goal is to draw the straightest line possible that goes right through the center of the data. That's a really bad straight line, but hopefully you get the idea. And the goal is to try and make the square so the distance, that point's right on the line, this point slightly off the line, that's the deviation. And if you were to square that, you would take that deviation squared. And then this one, you would take that deviation squared. And then this one, there's that deviation, and we want to make a square out of it. You should be doing this on your paper as well because you have this graph on your paper. And we want to get that square. And then over here, we want to make that a square. So we take our deviation, the distance from the point to the predicted line, and we square it, and then we add all those up. And the goal is to get those squares, if we add them all together, the goal is to get them to be as small as possible. Now, least squares is the most common, but it's not the only method. So there are other methods in other classes that you get to, but in our class we're going to focus on least squares regression lines. The slope. For every unit increase in x, there is an approximate, and the key phrasing there is approximate. Make sure you include that. There is an approximate increase or decrease of b values in y. And the correlation coefficient is, remember we talked about this in the previous video, you want to talk about the direction, the strength, and the form. So is it positive or negative? Is it strong or moderate? Is it linear or not? Alright, so here's a data set. I want you to put this into your calculator. Put the x into list 1 and the y into list 2. And what this data set is, it gives us the ages in months and the heights in inches of 7 children. And once you put them in, you have them in your list. The next thing that I want you to do is go into your stat menu, over to calculations, and you want to do linear regression ax plus b, or a plus bx, whichever one your calculator has, and that will give you the least squares regression line. You can also do a scatter plot if you go up to stat plots and you turn the scatter plot function on, and then you press its graph and it should graph it for you. Once you've found the least squares regression line, and this is the way we're going to do it most of the time, is we're going to put them into our calculator, and we're going to let the calculator do the work for us. Then the question becomes, can you interpret the slope and the correlation coefficient in context? So hopefully by this point, with all of my talking, you've been able to put these into your calculator and you've been able to find the least squares regression line. Here is, using Fathom, which is a program we have in our computer lab, here's what the scatter plot looks like, and then here is the least squares regression line. And you can see that it puts it into words for us. So the height, the predicted height, equals 0.342 times the months plus 20.4. So the 0.342 is your slope, and the 20.4 is your y-intercept. And Fathom gives you the r-squared value. It does not give you the r value. So on Fathom, you would have to actually use your calculator to do 0.99 and take the square root. On your calculator, it should have given you the square root, which was 0.994. So interpretation-wise, what you would write is you would say that there is a strong positive linear association between the age and the height of children. Strong because it was 0.99, positive because it was going upward, and linear because it made a straight line, and then the context between the age and the height of the children. For slope, you would say for an increase in the age of 1 month, so in other words, for every 1 unit increase on the x-axis, there is an approximate, circle that, that's very important, approximate increase of 0.34 inches in the heights of children. Here's that exact same problem. So your data is still in your data set. You should have your equation written down somewhere. And now we want to predict the height of someone who's 4.5 years old. Well, the first thing we'd want to do is change that 4.5 into months. So that's going to be 54 months. Plug 54 months into your equation and use it to make a prediction for the y value. And then do the same thing to predict the height of someone who is 20 years old. 20 years old would be 20 times 12, 240 months, and you'd want to use that to make a prediction. Now here's our graph. You can trace over and you can find out where is approximately 54 months, and you can see that for 54 months the prediction would be that the height is approximately 35, 37 inches tall. Now 240 months is off the graph, so that's called extrapolation. Okay, I mentioned extrapolation earlier. Extrapolation is the least squares regression line should not be used to make a prediction, predict y value for values of x outside the data set. For our previous example, where we were trying to predict the age of someone who's 20 years old based on that equation, we can't make that prediction because none of the data that we have actually is within that data set, and it also doesn't make sense. Most people stop growing once they reach a certain age, and they start leveling off. So an extrapolation in that case, you wouldn't want to use any kind of line based upon an early, based upon young kids to make an extrapolation, because otherwise you'd have 45-year-olds who are 10, 12 feet tall. So we can't do that. It is unknown whether the pattern observed in the scatter plot continues outside this range. We simply don't know what happens when we're doing extrapolation. Maybe the pattern changes, maybe it curves, maybe it levels off. We don't know. So extrapolation is not a good idea. Don't want to do that. You want to try and avoid it.
That's all, folks.